Hi everyone, my name is Ira Mushtaq and I will be presenting my project Simulate Cardiac MRI Performance for First Pass Perfusion using MRXCAT Digital Phantom. The reason I chose this project was I wanted to learn digital simulation of tissue mask as they provide a gold standard for evaluation. I also wanted to learn cardiac first pass perfusion because I believe it can help me for my research later on. There are three aims of this project. First is to simulate 3D perfusion at MRXCAT on MRXCAT at high field 3 Tesla, and then simulate perfusion on low field at around zero point 0.5 Tesla, and then compare their performance. Overall, the motivation of using first pass perfusion is to detect coronary artery disease, which is the leading cause of death in the world. It is basically caused by atherosclerosis, which is a kind of lipid accumulation inside coronary arteries. It negatively affect the blood flow, so heart muscle gets less blood, which affects its health. So, how first pass perfusion helps in detection of CAD? First pass perfusion is a myocardial perfusion imaging technique in which a contrast agent is injected into the heart, and after the injection, MRI images are acquired. When MRI images are being after MRI images are acquired, quantification is performed or signal intensities in the region of interest are measured to detect if there have been any perfusion defects. The goal of this project was to simulate first pass perfusion at low field. There are different low field simulators available, but they work for proton density weighted imaging. However, we wanted to use MRXCAT for flow imaging, which is T1 weighted, so that cannot be used here. So the reason behind using MRXCAT was it basically provides a gold standard. It also provides a diversity, like you can simulate systole, diastole, or you can change the body weights or like different anatomies. So it is quite diverse in its applications. Overall, the methods used in this project are like three to four, but the first step, uh, not the method, it's the step. So the first step is to create tissue mask. So I used XCAT to create 3D volume, and after the creation of 3D volume, I computed AIF contrast agent concentration in myocardium and R of F. Um, AIF is basically determines the contrast agent input to a myocardium. So this is the input to the heart muscle, and this is the output of the heart muscle. And we want to know what was the response of the heart muscle. So we deconvolve this AIF with C of myocardium, and we get the response of the heart muscle. Uh, right, the response of heart muscle means what was the fraction of unit bolus after time t. So how much it contained and how was the flow, right? So in order to make our simulation realistic, we modeled it with real time with the research mentioned as cited as a first reference. So they have used this AIF and this C of Mayo, and I tried to make these quite close to them and then computed R of t. So my alpha and beta values for my Fermi function, which models R of t, comes out to be 0.2. Um, After modeling flow, I had to update flow concentration at each time frame. So overall, what happens is blood first enters into right atrium, then right ventricle, then it goes to lungs, and after that it enters left ventricle and left atrium, left ventricle, and then it goes to heart muscle. So in order to perform the real time imaging, I had to update the flow concentration at each time frame, and then I had to acquire signal intensities. For acquisition of signal intensity for first pass perfusion, there are two steps. First is the preparation of the magnetization, which involves a saturation recovery, which involves a 90-degree non selective pulse application, and then there is a crusher gradient. And after the application of crusher gradient, magnetization recovers based on the T1 value. So as contrast agent shortens the T1 value, so it recovers faster. After signal intensity calculation, I added noise to make simulation realistic. For the calculation of results, the first step was to calculate the gold standard, the most ideal case, so which is like 1 cross 1 millimeter. So this is the slice thickness and this is the in plane resolution. So it is ideal, it is without any noise. And then I consulted this paper, which suggested an SNR of around 17 after contrast agent in myocardium. So in order to make contrast agent concentration around 17 here, which is around 2.3 now, I had to make standard deviation. I calculated standard deviation to be 0.13. After the calculation of standard deviation, I simulated high field and low field data. For high field, I kept this standard deviation, and for low field, my standard deviation of noise was 0.81. Likewise, R1 was 5.6, and R1 relaxivity increase at low field, so it was around 0.61. Before displaying the video, we can see that the background here appears brighter as compared to this one. This is because the T1 of fat is shorter at low field. Overall, if we see the performance, we can see that SNR has drastically reduced at low field. So it is even below than 5 SNR, and at high field it is around 17, so which is comparatively very high at high field. Overall, if we compare the results at high field and low field, we observe these trends. So first, overall signal intensity has increased in left ventricle and myocardium. The reason is T1 values are shorter and relaxivity is also making them more shorter. So our T1 weighted imaging makes the signal intensity more higher. But the standard deviation is also very high at low field because the noise is directly proportional to B naught. As B naught decreases, standard deviation goes up. Therefore, we obtain lower SNR and CNR. Our signal intensities, however, are higher, but we also observed non-linearity, which is a major concern of first pass perfusion. So what is non-linearity thing? It is basically we in order to quantify our results accurately, we acquire linearity between contrast agent concentration and signal intensity. Like in the way contrast agent concentration moves, our signal intensity should also reflect the same thing. But at higher saturation time, we do not get this linearity. However, we get higher SNR. It is around at 17, but at low saturation time, which is the time between the application of saturation recovery pulse and the data acquisition, we get comparatively low SNR. So there is a trade-off. If we get linearity, we have to compromise on SNR and CNR, and if we want to acquire higher SNR, we have to compromise on non-linearity. And the second challenge of just mention one last thing. So we see that as compared to high field, the non-linearity trend at low field is very high. So it will have challenges in quantification. Okay, overall the second challenge of this project was XCAT data acquisition. So XCAT, so as it was 3D volume, and so it was quite difficult to manage the data. It became difficult to manage the data sometimes. So overall lessons learned: I learned AIF fitting, I learned the extraction of signal intensities from my image. I also learned overall the flow of first pass perfusion and how it can be beneficial for CAD detection. That's all from my side. Thank you.